Well, good evening. We are doing a very unconventional sort of way of starting the lecture tonight, so you all have your some goodies with you and sitting comfortably. Just don't fall asleep. But I am very excited about tonight and what you will be hearing. And thank you so much for being here. It really means a lot to not only to the speakers, but also to me as the president of the Westmont chapter of Phi Kappa Phi National Honor Society. Despite the weather, really grateful that you are here. So welcome officially to the Spring 2024 Paul C. Wilt Phi Kappa Phi lecture. As I mentioned, I am Helen Rhee in Religious Studies, president of Westmont chapter of Phi Kappa Phi National Honor Society. Founded in 1897, Phi Kappa Phi is the nation's oldest and most selective multidisciplinary collegiate honor society. It recognizes and promotes academic excellence in all fields of higher education and engages the community of scholars in service to others. The Phi Kappa Phi Paul C. Wilt lecture series was founded to honor longtime member of Westmont History Department, the late Paul C. Wilt, and to showcase some of our finest academic work for a general audience. This lecture series has long provided some of the high points of our public scholarship, and it is unique in that, in addition to the main lecture, two faculty members give each 10-minute responses. So I will first introduce tonight's main lecturer, Dr. Jan Ito, and then the two faculty respondents, Dr. Jim Taylor from Philosophy Department and Dr. Bob Haring-Kaye from Physics Department. Dr. Ito's lecture will last about 40 to 45 minutes and will be followed by the two responses. After Dr. Taylor's and Dr. Bob Haring-Kaye's responses, Dr. Ito will briefly respond to them, and then I will open up a floor to receive any questions from you all. So let me first introduce tonight's main lecturer, Dr. Jan Ito. Dr. Ito joined Westmont as an assistant professor of physics department in the fall of 2022. She is a native Southern Californian, born and raised in North San Diego County. Having been blessed growing up in a rural area, she naturally decided to study astrophysics after many nights staring at the night sky. Dr. Jan Ito received her bachelor's in physics and astrophysics from UC Berkeley, and her master's and PhD in physics from UC San Diego. She has been to Chile many times to deploy the telescopes that she's been working on, and as a graduate student, she was part of a small team that led research and development of the telescope camera that is now on a telescope in Chile. Dr. Ito's research interest has migrated from studying galaxy evolution to studying cosmology, which she will be sharing more about tonight. She also enjoys philosophical lines of thought, and she finds those philosophical inquiries fitting, as she would claim that physics and philosophy would be described as two sides of the same coin. Our first respondent, Dr. Jim Taylor, is professor of philosophy at Westmont and specializes in epistemology, philosophy of religion, and Christian apologetics. He received his bachelor's in philosophy at Westmont, a master's in theology at Fuller Theological Seminary, and a PhD in philosophy at the University of Arizona. Prior to joining Westmont, he taught at Bowling Green State University in Ohio, and Dr. Taylor has published a number of philosophical essays in professional journals. He has also written 3 books. First, Introducing Apologetics, Cultivating Christian Commitment. Second, Learning for Wisdom, Christian Education and the Good Life. And third, with his wife Jennifer Moe Taylor, soul pilgrimage, knowing God in everyday life. Our second respondent, Dr. Bob Haring-Kaye, he joined the Westmont faculty in August of 2020, and he specializes in teaching introductory physics and laboratory-based courses at all levels. He earned his bachelor's and master's degrees at Florida State University before completing a doctoral there in nuclear physics. His primary research interest focuses on the structure of atomic nuclei at the limits of spin and binding, deduced from gamma-ray spectroscopy, and he thoroughly enjoys involving undergraduate students in that research. Dr. Haring-Kaye has been a principal or co-principal investigator on 4 National Science Foundation grants. The last 2 of them focused on cultivating research experiences for undergraduate students. So without now further ado, then let's welcome Dr. Jen Ito.
Good evening, and thank you, Helen, for that lovely introduction. Thank you all, again, for being here tonight and braving the cold and the rain. I know I was surprised with how much it started raining. What was that, like 4 o'clock or something like that? It was just dumping. Anyway, one of the reasons I am particularly excited about tonight's talk is not only do I get to share about the science behind my research, but I also get to share about the integration of other fields with physics. So as Helen mentioned, my research area is in cosmology, specifically instrumentation cosmology. So basically, I work on telescopes that study the origin and evolution of the universe. So that's the definition that I'm going to be working with. However, historically, cosmology has also had a second definition. It was also, I guess, a field of philosophy, metaphysics, right? So in the definition that you see behind me from Merriam-Webster, the first one is split into 2 parts. A branch, right? First, it's a branch of metaphysics, or it is a theory or doctrine describing the natural order of the universe. And I apologize, I was originally going to have my computer right here, but I don't have a Mac, so apparently the HDMI cable at the front here does not work, so apologies for that. Second definition of cosmology, though, here is probably what we may be more familiar with, and that is a field of astronomy that studies origin, evolution of universe, galaxies, things like that. So what I am going to do in this talk is start off with describing the science side of cosmology and then look into the philosophical side of things. So I'm going to be looking at the current standard cosmological model, and I say current because this is something that has been constantly changing. Right? One of the biggest aspects that's been added to this model is only like 40 years old, so 1980s, right? So it is constantly evolving, and when you think about how long people have been thinking about cosmology, it's really a very young model. So we're going to start from the beginning, and we're going to step through major parts of it. This is going to be a very quick overview of the standard cosmological models. So, yes, the slide behind me you see is blank. That is on purpose. Because, right, at the very beginning, it is thought that this event known as the Big Bang happened, where you have basically the origin or the beginning of the universe. And on these next, 7 slides or so, what I'm going to have is you have the time or the age of the universe in your upper left. Yes. And then the name of the event in your upper right, or the name of the era. And sometimes there'll be a temperature down here on the bottom left, rough guesstimation of what the temperature of the universe was at this time. So T equals 0, Big Bang. Depending on who you talk to, they'll say that it was just an event at T equals 0, the beginning of time, or they'll say it's actually something that's currently happening now even. But for the purpose of this talk, I'm going to use it as a single event that happens at the beginning here. So right after the Big Bang, it is thought that you have the existence of what we call the fundamental particles. And so these are the particles that end up becoming protons and neutrons later on. And the temperature is just very, very hot. It is at a temperature range that we cannot duplicate right now. It is, I think it's something on the order of like 10 to the 26 degrees Kelvin, something like that. So very hot. Now, shortly after this instance, where you kind of have this particle soup, there is the thought that this event known as inflation happened, and this is less than fractions of a second. Right? I think it's what did I say? 10 to the minus 35 to 10 to the minus 32 seconds. So that is, what is that? 10 to the minus 35, right? That's 1 with 34 zeros in front of it. So very, very fast. And it's thought that inflation, right, took the universe and basically expanded it by a factor of 10 to the 26. And so now you have still a very hot universe, but is now very much expanded and much, much larger than what it was before this inflationary event. 3 minutes after now, there is a process known as Big Bang nucleosynthesis. So this is when your fundamental particles then now become your protons, your neutrons, and your atomic nuclei start to form. And the only ones that are thought to be formed in this time is you have your hydrogen nuclei, right, which is just a proton. Then you have your deuterium, helium-3, helium-4, and some schools of thought will say lithium-7 also. But those are your what we call in astrophysics, those are your light elements, and everything after that in your periodic table is known as metals. And this always makes I don't know if that makes the chemists roll their eyes or what, but definitely not how they define metals. But this is the reason why astrophysicists, astronomers define metals this way, is because the initial atoms were only the very light ones, so you have hydrogen, helium, basically. So now that we have these nuclei, we're going to fast forward hundreds of thousands of years now to an era called recombination, and I put re in quotes for a reason. Up until this point, the universe was still so hot that you don't have any stable atoms. So you have your protons, you have your atomic nuclei for helium, but the electrons, when they try to bind to those nuclei, they automatically get knocked off by high energy photons. So you don't have any stable atoms. However, when we get to this era of recombination, the universe has expanded enough and cooled enough that the electrons are no longer being knocked off. So now you have these stable atoms that are forming. So that's where I guess maybe the term recombination comes from. This really is the first time you get your stable, like really stable atoms. So, but it's termed recombination. So we stick with that. Now, also what happens during this time is that the universe goes from being something that is opaque to something that is transparent. And basically all that means is that the photons, the light particles, are able to travel farther. Before recombination, there was so much matter, it was so dense that the photons were just bouncing off of everything and couldn't travel very far without running into something else. So when you have your atoms forming then, the photons, the space is less dense, photons can travel farther without running into another object. And let's see. Next is, so jumping now, what did I say this was? 200 million years, there we go. 200 million years, it's thought that this is when the first star formation happens. So these stars would be considered what we call population 3 stars. So these are stars that only contain hydrogen and helium. And then from nucleosynthesis that happens in their core, they explode. You have heavier elements now in the universe, and then those would generate stars with heavier elements now, and that process continues until you end up with your more, say, metal-heavy stars, population 2 stars, and then the stars that we see now that are the heaviest or have the most heavy elements, which are your population 1 stars. So population 1 and 2 stars have been observed, but we have yet to see a population 3 star. So still looking for that. Jump forward, I think another, 100 million years or so, not sure yet. There's a question mark here. And maybe some of you have been keeping up with the James Webb Space Telescope discoveries. This is one of the galaxies that they discovered last year, and it is considered, I believe, one of the 4 oldest ones, named Maisie's Galaxy. Excuse me. So it's thought that galaxy formation could have happened as early as 300 million years, but as we increase with technology and are able to see farther out in space, farther back in the past, who knows what we're going to find. So, and then that brings us a giant leap to today. So we have 13.8 billion years later, we have all the galaxy structures that we see, planets, stars that we can observe, and all those beautiful pictures that we see coming from different space telescopes. This picture that I've put up is a picture that I took when I was in Chile during one of my research trips. It was just really, really special to see different constellations that you don't get to see in the Northern Hemisphere. And also, you could see small and large Magellanic Cloud. And so it was just a very neat experience to be able to see all of that. So that was a very quick overview of the current standard cosmological model. I know that I just touched on the highlights, but what I want to focus on is this is a part. It's a part of the model, and that is the part that my research work focuses on. So there is a very long and quite fascinating history of how we came to establish this as the standard cosmological model, but I'm going to only pick out one part of it, and we're going to start with the cosmic microwave background. So this is an artist's rendition, that artist being me, of what the CMB would look like. Because it is not in the optical spectrum, we can't see it with our eyes. It is millimeter wavelength light, and so it is radiation that we see all around us, and it was discovered early 1960s by 2 astronomers, Penzias and Wilson, who were working for Bell Laboratories. And when they discovered this, there was some back and forth, what could this be? And they were connected with a theorist from Princeton who had created this model saying that, if this happened in the past, we should expect to see something like this relic radiation at 5 Kelvin. And so what they measured, at that time, what they measured I think was closer to 3 Kelvin, but more experiments have been refining that number. So now we measure the temperature of the cosmic microwave background to be 2.725 Kelvin. And you can think of this kind of as the temperature of the universe, basically. So this was, this is considered one of the greatest evidences for what is now considered the Big Bang model. But when it was first discovered, there were some problems. So if you remember that time I mentioned called inflation, where the universe expanded a lot in a very short amount of time, that wasn't developed yet in the 60s. So you have this radiation, but there are some problems with it. So first one is what they measured of the CMB is that it was a very constant temperature across the whole sky. It's very uniform, but the problem with that, known as the horizon problem, is that the universe is so vast, there's no way, even in the time of the age of the universe, that opposite points of the sky could have thermal equilibrated. They couldn't be the same temperature. So that's the first problem. Second problem has to do with something called the geometry of space-time. Now, if this is confusing, don't worry, it's confusing for me too. So, the best way that I've thought of to try and explain it is if you were to pretend that we were to take our three-dimensional space and somehow make it two-dimensional, and then that would be the surface of either the sphere, the saddle-looking shape, or it would be completely flat. So those are three different geometries or curvatures of space-time. And if we were living in either of them, right, we wouldn't be able to tell just by looking around us which geometry we're in, because we'd be such in a localized spot, it would look flat around us. So there are other metrics that would need to be used to determine whether or not we were on either of these geometries. Based on analysis from the CMB, cosmologists concluded that the geometry of space-time is flat. However, the problem with that is essentially a fine-tuning problem. So for it to be flat now, it would have had to have been flat at the beginning, and that's a very, very special set of circumstances for that to happen. So if there was any deviation from it being flat, it would have turned into one of the other curvatures because of the expansion of space-time. So that's the second issue there. Third one has to do with something called the magnetic monopole. So this is a particle that is predicted by Big Bang cosmology. It should be abundant, but we haven't detected any. So open question there. Now, I mentioned that there's this idea of inflation that hadn't been developed yet, but it was developed to try and answer this monopole problem, and it was expanded to be able to answer the other two as well. So how does it do that? So for the horizon problem, what it does is it says initially, before inflation, the universe was small enough where it could be in causal contact everywhere could be in causal contact. So you could have something that was all the same temperature. And then right after inflation, those points were expanded so that they're very far away and no longer in causal contact. However, it happens so fast that they are still at the same temperature as each other. So that's how it addressed the horizon problem. The second problem, the geometry, right, the flatness of the universe, inflation would take any sort of arbitrary geometry and through the expansion would make it basically flat. And then with the monopole problem, the thinking is before inflation there could have been a lot of these magnetic monopole particles, but then inflation would have basically lowered the density so much that we're not able to detect them yet, at least. So those are the three ways basically how inflation addressed the issues that were coming up. But the question is there actually evidence that would be consistent with this? And that is where more the research work that I did comes in. But first, I'm going to talk about the observable evidence that we would have for inflation. So inflation predicts perturbations in what's called the gravitational metric. This is basically just, it has predictions on how your energy interacts. And so there are two different kinds of perturbations. One is a scalar perturbation and the other is a tensor perturbation. So your scalar perturbation has to do with density of matter, basically. And then your tensor perturbation has to do with gravitational waves that were generated from inflation. So there are three three lines of evidence, basically. So for your scalar perturbations, you have temperature anisotropies in the CMB, and then you also have E-mode polarization of the CMB. And then for your tensor perturbations, you would have your B-mode polarization. So we're going to step through each of these, looking at the CMB and seeing what it has. So I mentioned, right, that the CMB on average is 2.725 degrees Kelvin, and it looks pretty uniform. But if we were to subtract that average temperature, we'd actually end up seeing what you see behind me. And this might actually be something that might be a little bit more familiar, because this is typically the map that we see when we talk about the CMB. So these are very, very tiny temperature fluctuations. If you see the color scale is plus or minus 2 times 10 to the minus 4, so that's 2 10,000ths. And so we can take this temperature map and do a Fourier transform in space. So basically what that means is we're going to look at different angles on the sky and see how the temperature differences correlate. So that's where we get our CMB temperature power spectrum that's shown here. The x-axis can be a little confusing, so the smaller values of L on your x-axis, so your left side, is large angular scale, so it's looking at large patches on the sky. And then your high L is looking at small patches on the sky. And you're looking basically at the strength of temperature fluctuations on those different scales. Each of these peaks that you see, scientists have also been analyzing, and they say different things. So for example, that first large peak speaks to the flatness of space-time. And also I should add, sorry, the blue dots here are the observed data points, and then the red line is the theoretical curve. So you can see it matches pretty well, and then at the bottom plot shows you the residual, or the difference between them. So with this study, then it was concluded that yes, we do see the temperature anisotropies that would be predicted with inflation. So got that one checked off. Next one is polarization. So light can have directionality to it, and so the CMB can also be polarized in that sense. And it can be what's called linearly polarized, and this is from two things: combination of what's called a quadrupole temperature anisotropy and Thomson scattering. So basically what you have is you have 4 different regions. You have 2 regions that are hotter and 2 regions that are colder on opposite sides of each other. That is depicted by the blue and red crosses that you see. In the animation, it is only half of the quadrupole, so you see 2 of them. So you can imagine there's another blue photon coming in from this side and another red one coming up from there. But they basically excite the electron, and the electron emits a photon that is linearly polarized. Now, this polarization can be broken down into two parts. So it can be a part that is divergence-free, which we call that's the B mode, and then curl-free, which is the E mode. And so that's where the 2 different kinds of polarizations come from that were on the previous slide. So do we see that? This is a summary slide of what we have measured as far as CMB polarization. So at the very top, that black curve, that is the temperature power spectrum that you saw earlier. The blue curve, yes. Blue curve is your E-mode power spectrum. So that is your E-mode polarization, and that is what has been observed so far. So we do see that signal in the CMB. The solid red curve is known as the lensing B mode. And so this is actually a result of the E mode, CMB E mode, polarized light being gravitationally lensed as it travels through space and turning into your B mode CMB polarized light. And so this is kind of an extra B mode signal. The one that we would be wanting to see that would be evidence of inflation is the red dotted line that you see. That is named here the primordial B mode. And I realized I forgot to click through some things here, so I'm going to click through. So your E mode polarization, right, we talked about how you have that quadruple anisotropy. You have 2 regions of hot and 2 regions of cold. So that, for the E mode polarization, is generated because of areas of less dense and more dense gravity, basically. I mentioned how the, I mentioned how the, how E modes can be gravitationally lensed into B modes, and then for the primordial B modes, the quadruple anisotropy is developed because of the gravitational wave, and so the gravitational wave will stretch and squeeze space, which then creates your hot and cold temperature differences, basically. So far, we have pretty strong evidence for the scalar perturbations predicted by inflation. What we're still looking for is the tensor perturbations, or the B-mode polarization from gravitational waves caused by inflation. So that's where the project that I work on comes in. So trying to find this B-mode polarization is a pretty hot topic in cosmology right now. This is what a lot of the telescopes being built these days are trying to do. And it's almost like a race, trying to be the first ones to find this. But no, really, we're all very friendly and supportive of each other, honestly. So that's nice. So this is a picture of the Ceratoco Plateau in the Atacama Desert in Chile. The telescopes that I work on are called Simon's Array, and it's those 3 telescopes that you see highlighted by the box there. So 1, 2, 3. And yeah, we share the plateau with 3 other experiments, all with the same or similar science goals. This project, though, Simon's Array, is built on a previous project known as Polar Bear. And yeah, project names in astrophysics can be quite fun sometimes. So Polar Bear is a pretty cute one. This project used a Huantran telescope with a cryogenic receiver. Cryogenic receiver is just fancy words for a very cold camera. And this camera is huge, right? It's big enough that I could fit inside of it. It's shaped like a DSLR, so you've got a cylindrical lens part, and then you've got the box part. The cylindrical lens part is probably like 7 feet long and 3 feet across. And so it's a very large camera. And we have it under vacuum and cooled so that, because of the detector technology that we're using. So this first telescope had 1,274 detectors focusing at 150 gigahertz. It started observations in 2012, and I believe it did something like 5 seasons of observations. So building on this then is the Simon's Array, and so this was an expansion, adding 2 more telescopes. And in addition to adding 2 more identical telescopes, we also iterated on the cold camera. So it's a 2nd generation cryogenic receiver. And Polar Bear, so they were all named Polar Bear 2A, 2B, 2C. Polar Bear 2B is the one that I worked on in my graduate work. I was the part of the team that Helen mentioned. We worked on building the cryogenic receiver at UCSD, testing detectors, working on integration, and deploying it to the site. So now, question is, why in the Atacama Desert? So if you were to go to Google Maps and actually type in, what did I say, polar bear? Oh, Simon's Array, Chile. Simon's Array, Chile, you'll actually find us. We are at 5,200 meters or 17,000 feet. That is about half atmosphere, so we do wear oxygen, or at least we should wear oxygen when we're up there. The reason why that we work at that elevation in this particularly dry place really has to do with the amount of moisture in the air, actually. So we don't really care about light pollution that much because the signals that we're looking for are not optical. So we can actually observe when the sun's out, which is actually a perk. But we do care about water in the atmosphere because water can generate unwanted noise and it can actually absorb the signal that we're looking for. So I have a picture here, a graph, that shows the transmission versus light frequency. So transmission, so one, it means that the light can come completely through the atmosphere, and then you have multiple plots of different levels of water vapor. So on average at the site, we have less than 1 millimeter PWV. So, but it also means, if you notice, there are kind of these windows where we have a lot of transmission. And so actually it's pretty convenient that the signal, the science signal that we're looking for is within those windows, and we designed our detectors so that we could take advantage of those windows. So our detectors are designed such that their center frequency is 90 gigahertz, and then center frequency here is 150 gigahertz. So yeah, as was mentioned, I have been down here, down to the site multiple times, all of them working with building the receiver down there, putting it on the telescope, and then also continuing to commission it and get it working, basically. But there are some other things, too, that we had to do. So last year, I went down with my 2 research students, and some of you probably recognize them. We have Jacob Nelson, the tall one in the middle, and then Michael Liu, right, is on the left side. These 2 were very adventurous, came down with me for a month, and we worked on the telescope and did various different tasks. So some of the things I show here, so on the left, you see Michael working on an enclosure for the telescope camera. So even though we are in a place that is very dry, as you can see in this picture, it still snows. So we need to protect all the electronics in our telescope, and we have had problems with water before. So we worked on, while we were down there, we worked on building an enclosure. There's an enclosure to protect the electronics, to protect the camera from the elements. On the right, you see Jacob working on a calibration piece of equipment. So this is basically a thermal source. It's a heat source that we point at our detectors to do a thermal calibration. Since basically we're measuring temperature on the sky, and the data that we get is electrical readings, current readings, we need to be able to determine basically what, if we measure a certain temperature, this is the current that we're going to read, so it's that kind of calibration. And so he was working on the thermal source because there was an issue with it when we were down there. So various other aspects of the project, maintenance that we have to do. We are still in the calibration phase and trying to get it on Sky for Science. But yeah, one thing with experimentation, what is it? The best laid plans of mice and men. So also teaches you to be patient. But that is, yeah, that's what I wanted to share as far as my research work goes, and the science side of cosmology. Now I would like to transition into the philosophy and faith side. Again, I think this part is fascinating just to see how cosmology has aspects that are related to both science, but also like metaphysics and philosophy and faith, really. So I'm going to start off with this quote, and I apologize for mispronouncing this name, but this author, Helge Krag, has his PhD in physics and philosophy. He is also a professor of history of science. In 2019, he won the American Physical Society Award for History of Physics for contributing to history of cosmology and quantum physics. And he wrote this chapter of a book titled The Cosmology and the Origin of the Universe, Historical and Conceptual Perspectives. And in here, he gives a really thorough overview of how cosmology initially was a field under philosophy, a field under religion more, before it became a field of science. And so his quote here that cosmology wasn't really a field of science before World War I kind of shows how new and how young this field is, especially in astrophysics. So wanted to explore some aspects of cosmology that are more philosophical in nature. So I have listed here 3 examples. There are more, but I figured I would stick to just these 3, and I'm going to hone in on the cosmological principle. So the first one, the uniqueness of the universe, right? We cannot subject our universe to experimentation, not in the sense of we can't grow it in the lab. We can't test hypotheses about how it began, and we also can't observe other universes, at least that we know of so far. Excuse me. And right, then there's this question of, can we actually have laws of the universe then if we only have one, right? Second bullet point I have here is scale of the universe. So the idea behind this one is that, right, if our universe is actually infinite, we only have a finite window, we cannot actually observe the entire universe, and so we can't make any empirical measurements. So any extrapolation that you do would be more philosophical in nature rather than empirical. And then this last point, the cosmological principle. This is originally derived from the Copernican principle, which can be described by the quote that I have here. This is a quote by Andrew Little in one of his, it's a nice little textbook, An Introduction to Modern Cosmology. I was trying to remember whether I got this textbook in grad school or undergrad, but it was one of those two. And he opens the book with this quote. The cornerstone of modern cosmology is the belief that the place which we occupy in the universe is no way special, right? So this is a rewording traditionally known as the Copernican principle, that there is no unique spot in the universe, basically. Now, to build on this, we get the cosmological principle, which is basically that the universe is isotropic and homogeneous. Those are kind of the 2 words that we use. Basically what that means is that it's isotropic, so there's no preferred direction, and it's homogeneous. So on large scales, it basically looks the same. Now, there are evidences that this is true for what we can observe around us, right? CMB being one of those evidences. But to extrapolate that and say, oh, this is the rest of the universe, that is more of a philosophical and a faith-based statement. We also use this, though, we use this presupposition to build the models that we have. So an example is when we're trying to derive the space-time geometry of the universe. So what I have here is Einstein's equations, and the first one, the top one, is a rather complicated one, at least I think it's complicated. If you notice, you have these variables with indices. And basically that means that there are 16, in this case, there are 16 different values that that variable can be. When we apply the cosmological principle, we reduce it down to 1. And so this is also the easiest way to be able to solve these, well, I don't want to say easiest, simplest way to solve these equations. The interesting thing here is that when we use the cosmological principle, it can apply to multiple different kinds of geometries, and you actually don't need it to solve these equations. So there is a certain undeterminism about it where you can have these models with or without the cosmological principle, but it is something that we choose to apply. So again, how we make these presuppositions based on what we can see locally. That's true, but it still is something that we have to extrapolate to the rest of the universe, which is not something that we can prove. I want to come back to this quote. And I like how Little wrote this statement. He says the word belief in there. I don't know what he meant by that, but maybe he understood the assumption that we make in this statement. And one thing too with this, when we talk about cosmology, when we talk about for instance, with the Copernican principle, right? It's easy to extrapolate that into something more than just the physical realm, right? One might extrapolate that into talking about the meaning of life, right? If our physical location is in no place special, what does that mean about our existence, right? But again, we have to be careful with that, right? Because we're taking something that we are observing, something from the physical realm, and extrapolating that into the metaphysical. And so it's interesting, there's an article that I found way back that I've kept coming back to because I've really appreciated it. It's from the Stanford Encyclopedia of Philosophy. And it's written by 2 authors, one of which came up with this differentiation between cosmology and a word, cosmologia. And he differentiates these two by saying cosmology is the science side of things, so that's what we observe. And cosmologia takes those findings and extrapolates them to things like meaning of life. And so this is a quote that I thought was very interesting that they have at the end of their article. And I am going to step away from the mic so I can read this, and hopefully I will just say it loud enough. I think what I really appreciate the most about this quote is understanding the limitations of science, right? I guess I feel like in this day and age, there are a lot of great things that science is discovering and advancing, but we also have to remember that it is still limited to this physical realm. So I am going to close with this quote that I found very amusing about cosmology. Thank you very much.
Good evening, everybody, and thank you so much to Jen for inviting me to be a commentator. Not a scientist, a philosopher, but of course, as she is just indicating, she's opening this up to an interdisciplinary conversation, and quite an interesting conversation so far. Thank you for a very interesting and informative talk. Learned a lot of things from what you were saying. But since I'm not a scientist, as I said, I'm going to focus here on just philosophy and in particular the role of faith in cosmology. Cosmology more broadly defined, getting back to the very first part of her talk, looking at those definitions from the dictionary. And also the book that you were referring to, one of the books you're referring to about the history of cosmology, she's indicating that the scientific study is really rather recent, but thinkers have been wondering about the origin and nature of the universe for quite a long time, quite a number of centuries. Philosophers were thinking about the origin of the physical universe then well before the age of science. Plato thought that the cosmos was created by a divine craftsman that he called the demiurge, that brought order out of a pre-existing chaos. And so Plato had a sort of quasi-creationist account of where everything came from, but didn't really explain where the chaos came from. But there was chaos. This godlike figure then ordered it, and then we have not chaos but cosmos, an ordered physical reality on his view. But his student Aristotle, on the other hand, believed that the universe has always existed, and always existed in the same form that it does now, and that the role of God, the role of the divine being in Aristotle's philosophical system was not to bring everything into existence or even to order everything, but rather to keep things going, to explain why things keep moving. Everything, according to Aristotle, in the universe has built into it a kind of desire for the divine, and it's moving in order to get closer to God. So he had a way of explaining all the change in motion that we see, but not where things came from in the first place. So there then, in the ancient philosophical world, in these cosmological investigations, there was controversy, there was disagreement, and there has been, of course, from the beginning. As Jen's presentation shows, there are still disagreements of various kinds, but science, obviously, she's shown, has yielded an amazing amount of knowledge and a fair degree of consensus. Am I right that, certainly a lot more than has existed in the past? At least in general, still a lot of disagreements about specific things, about how the universe got started and how it came to be the way that it is now. So science is obviously a powerful tool in doing cosmology. Again, if we think of cosmology as how it started and how it got to be this way. But I want to focus on how Jen ended her discussion, the idea that even with all of this power, science also has limits. And I think it's important, as she agrees, to understand and acknowledge those limits. So my comments should be viewed as a friendly supplement to her talk rather than as a critical challenge. I'll leave that up to Bob here, perhaps. He'll do more science and perhaps more critical thinking, but I'm going to expand upon where Jen ended her talk with that emphasis on the limits of science. Well, first of all, empirical science, by its very nature, can investigate only what is observable. And that means it can study only the universe and the things inside it, because only the universe and the things inside of it are observable to us. If there is anything outside the universe, science isn't going to tell us about it because it's outside of the universe, outside of what is observable. Scientific cosmology can tell us what the initial physical state of the universe was and how the universe expanded and developed from that point. And that was really what Jen was going over in that very first part. But it cannot tell us what accounts for the existence of that initial state in the first place. Because if it had a cause, its cause, again, would have to be outside of physical reality, including the physical reality of space and time, interestingly. So whatever there might be before, you have to use the word before advisedly, because if time began when the universe began, there's a sense in which there was no before time. Never said it again. But it's a very, very perplexing thing to wonder what could be the cause of the universe in a timeless reality. Therefore, if a complete cosmological theory, one that explains everything we would want to know about the origin of the universe, if a complete cosmological theory would explain why physical reality of any sort exists at all, then science can't give us a complete cosmological reality. So science is forever going to be giving us cosmological theories, but incomplete ones on that understanding of what would count as a complete cosmological theory. Whether anything exists outside the physical universe, then, is a philosophical question. And from the beginning of philosophy in the ancient Greek tradition, philosophers have attempted to establish the existence of a non-physical first cause of the universe on the basis of what they've considered to be the observable contingency of physical reality. That is, on the basis of the assumption that the physical reality that exists doesn't have the resources to exist on its own. It isn't the kind of thing that has to exist. It's not a necessarily existent reality, but instead is the sort of reality that might not have existed. That's precisely what the word contingent means. Okay, it exists, but it might not have. It's possibly non-existent. And so then, with respect to something that is existing, but existing contingently like that, the question is, so why does it? And the classical philosophical cosmological argument with which some of you may be familiar, perhaps many or most of you, perhaps all of you, explains the universe's existence by appealing to an external that is outside the universe, non-physical, independent, that is existing on its own without needing something else to exist, necessary being, something that's not contingent, but rather is such that it has a nature that requires its existence. It's a sort of thing that would have to exist. And so that's the basic idea behind the so-called classical cosmological argument, often thought of as the cosmological argument for God's existence. But even if philosophical reason can establish the existence of such a first cause of the universe, and so can do something that empirical science can't, it still leaves a lot of important questions unanswered about the nature of this ultimate source of physical reality. Some philosophers think that the cosmological argument proves that the first cause of the universe is God, but there's more to God's nature than what's needed to explain the existence of the universe. So the first cause of the universe could be something other than God. And if a complete cosmological theory would enable us to identify the ultimate cause of the universe more specifically and unambiguously, then we'll need to look beyond both science and philosophy for that purpose. By the way, what could it be other than God? Well, it could be perhaps many gods. It could be Plato's demiurge, which falls short of being a completely, absolutely perfect being of the sort that we would think of as God. There are just too many alternative conceptions of what the first cause might be, even if we grant that it's a non-physical, independent, necessary thing. We think of God as being much more than that, even if God is at least those things. So again, even philosophy, if that's as far as philosophy can take us, will still leave questions unanswered about this ultimate source, ultimate cause of the physical universe. What we need to supplement science and philosophy is, I think, a special revelation from God. assuming there is a God. And of course, most of us, perhaps many of us, and maybe even all of us, believe that there is a God. And it would be nice to have some word from him to explain that he's there and that he is the cause, the creator of everything. And of course, that's what Christians believe we find in the Bible, a revelation that tells us more about the creator God's nature than we could figure out on the basis of philosophy alone. So science is limited in what it can tell us about the universe. Philosophy can tell us, not more than science. It can supplement what science tells us more about what might be out there to have caused it. But of course, we can turn to theology to tell us even more. Here's the thing, though. Reliance on the Bible as a source of knowledge will require that we supplement scientific and philosophical reason with faith, right? Because in looking to the Bible and assuming that it's the Word of God, a special revelation from God, we have to have faith that God is trustworthy and that what God reveals to us in Scripture is true. It's not something we can prove on the basis of reason, but have to take on faith. So you might wonder, does that mean that science and philosophy are superior to theology? Because science and philosophy are based on reason, and theology is based on faith. You might think that anything based on reason gives us a superior, more solid ground for our knowledge than something that is merely based on faith. Well, no, it doesn't mean that. It doesn't mean that science and philosophy are superior to theology just because theology relies on faith. All three sources of knowledge are based on assumptions that can't be established by reason and so must be accepted on the basis of faith. Science is based on various philosophical assumptions, for instance, such as the assumption that knowledge is even possible, an assumption that the philosopher Descartes felt he needed to defend in his meditations before doing science. That's what he's doing in the meditation, spending all 6 meditations establishing the possibility of knowledge as a basis or a foundation for thinking that when we do science, it can give us knowledge. So science then is built on philosophical assumptions, and so there's a sense in which science relative to philosophy, science has to rely on philosophy, so there's a sense in which science is based on faith in philosophy, you might say, faith in philosophical reason. And the cosmological principle that Jen mentioned in her talk, which entails that the laws of nature are the same in every part of the universe, is neither empirically verifiable, scientifically verifiable. I mean, after all, you'd have to see the whole universe. You'd have to observe the whole universe to see that every part of it was such that the laws of nature applied equally in every part of it in order to confirm it scientifically or empirically. Nor is it philosophically confirmable. I can't imagine some philosophical argument that would show that the universe has the same laws operative in every part of it. And even if this cosmological principle that entails, again, that the laws of nature are the same in every part of the universe, even if it were philosophically confirmable, philosophy itself is based on unprovable assumptions, such as the assumption that human reason, is a reliable source of knowledge. Now, the only way that you could establish that philosophically is by using reason itself to show it. And of course, that would be a circular argument, so you're not going to be able to do that. So even philosophy is based on faith. The upshot is that whether you're contributing to a cosmological theory as a scientist, a philosopher, or a theologian, and whether you're a theist or a non-theist, whether you believe in God or not, your theorizing will have to be based on assumptions that can't be proven. And if that means you have to take these assumptions on faith, then all contributors to cosmological theorizing are, in some sense, people of faith. Thank you.
Well, good evening, everyone. It's good to be here, and thank you for the opportunity to respond to Jen's talk, and thank you, Jen, for a really nice presentation. Really enjoyed it. Though I actually thought you might spell faith with a PH in a physics talk, but anyway, just kidding. That's an inside joke in our department. But at any rate, as a fellow physicist in our department, I will, in fact, focus on the science, but also I'd like to talk a bit about the integration of the science with a Christian worldview, because I find that to be just as fascinating, if not more so, than the science itself. So just this morning, I was talking with my students in our senior seminar course, which is exactly about the integration of faith and science. And we're talking about the Big Bang and some of its implications. And one of the things that we discussed was I think Jim touched on this, and Jen as well, but the Kalam cosmological argument. I didn't hear the word Kalam tonight, but I think that's maybe a broader term. Jim probably knows better than me. But it kind of goes like this, where anything that begins to exist has a cause. The universe has a cause. Therefore, the universe had to be, anything that begins to exist has a cause. The universe has a beginning. Therefore, the universe has a cause. So I think that's a pretty strong argument for a creator of the universe. It doesn't necessarily have to be the God of the Bible. Of course, that's what I believe, but I think it's a strong argument for a creator. So we discussed that a bit, and that was a fun conversation. But I'm also fascinated by how everything we see around us resulted from a single point in space, which actually is sort of a conundrum for me, because there's this thing called the uncertainty principle in quantum physics, which essentially says that you can't shrink things down to a single point and at least know what their momentum is. So I guess it could have infinite momentum at that singularity. But at any rate, if you figure that one out, I'd love to have a conversation about that as well. So there's some fun, kind of intermingling of quantum physics along with the cosmology that I find interesting as well. And then, of course, there's the whole statement in Genesis, which says, God says, "Let there be light." And I saw a lot of wiggles on your diagram there in the early universe, which I assume were the photons or bundles of light in the early universe. And by golly, there's your light, lots of light, in fact, at the beginning of the universe. So I see that as kind of a neat connection as well. Yes, there's a lot of details we don't understand, and I won't be going into that at all tonight, but I think that's a really cool way to point to the God of the Bible as creator. Another thing I find truly interesting is, as we look at the universe now, and again, thinking back to how it began as a single point in space, time, how is it that what we see around us leads to life as we know it? Basically, the idea of an anthropic principle, where things appear to be so finely tuned, such as to support life as we know it. So, for example, take gravity. If one were to imagine that gravity could be anywhere on this range of forces, the known forces in the universe, ranging from the weakest force, which is gravity, all the way up to the strong nuclear force. That's many, many orders of magnitude and strength. You can relate it to taking a tape measure, stretching it across the entire length of the known universe, and splitting it up into 1-inch increments. That's a long tape measure, by the way. Calculations have shown that if you adjust the strength of gravity by 1 inch on that tape measure, you basically screw up life as we know it. Things would either get crushed or they wouldn't coalesce the way they should to form life as we know it. So that's pretty amazing. Again, starting from a single point, and that's the granularity, that's pretty amazing. Take the cosmological constant, which was mentioned earlier in Jen's talk. This is essentially a measure of the energy density of the universe, which, as I understand it, sets the rate of either expansion of the universe or the contraction of it. This is actually pretty historically famous because Einstein wanted to eliminate it from his general theory of relativity, and I believe he later said it was the greatest mistake of his life. But at any rate, it's a small, I think this is right, a small positive value. And if one were to adjust that constant by, I don't know how many billionths, I forget the exact number, either the universe expands essentially out of control, or it shrinks back in on itself like an accordion, and again, we don't get life as we know it. A third really cool aspect as a nuclear physicist that I love is the ratio of the mass of the neutron to the proton. So this has to do with the nuclear engine that's happening in stars that basically generates the elements that we have around us, the nucleosynthesis that Jen mentioned. If you take that ratio, which I think is like, I don't know, 0.1% difference or something between the mass of the neutron and mass of the proton, and you adjust it by like just 1 part in a couple hundred, again, the nuclear fusion reaction rates get messed up, and we don't get the abundances of carbon and oxygen and such that are just slightly important for life. And so basically, these are just a few examples of how there's an immaculate fine-tuning of the universe to just cause a Goldilocks scenario to support us and to support life as we know it. And again, think of this as all sprouting from a single point in space. Coincidence? I don't think so. And then finally, my last observation, Jen, was I'm an experimentalist, so I love data. And you showed some very nice data, some CMB data. I often use that data as a evidence for the Big Bang. Talking with you before this talk, maybe I'm not as sure how strong of an argument that is, but I think it is a good argument from what I heard you say at your talk. And I just love it when seeing curves that match data really well, and you showed some really nice matching curves. So that was really fun, and I was very encouraged as a physicist, as an experimentalist, as a Christ follower, that this is even a strong foundation for my faith and with the science. So I just wanted to thank you for that. It was a big encouragement for me. Thanks so much.
Thank you both, Jim and Bob, for those very thoughtful responses. Let's see, I guess I'd like to build a little bit on what Jim mentioned as a small point that he mentioned about the difference of perspective between, it was Plato and Aristotle, I think, right? Interestingly enough, that's a conversation that actually is still happening, right? It's not a mainstream conversation, but there are many actually cyclical models of the Big Bang that are still discussed. I remember in grad school there were two talks by Sir Roger Penrose, who believes in the cyclical process of the Big Bang and then the Big Crunch, right? And it's basically, it is infinite in the sense that what happened before is the material that then seeds the next universe. So just wanted to add that while there is I'll say a general consensus of what the main, like what we call the standard model of cosmology, there still are other schools of thought that date all the way back to Plato and Aristotle, and perhaps further, I don't know. So, but no, thank you for your comments. Really appreciate it, and really appreciated that, that dialogue of physics, philosophy, and faith. So thank you. Bob, thank you for your comments. Yes, let's see, I probably am going to work backwards with your comments, respond to them backwards. Yes, so CMB is definitely evidence for, and I'm going to be very specific here, it is evidence for a radiation-dominated early universe. So that is, I think, probably technically historically how it was seen. It was originally thought by, George Gamow. He's the one who initially thought that the early universe was in this radiation-dominated era. Basically means you have, it's dominated by relativistic particles. And then there was a astronomer he was working with, Robert Haring from Johns Hopkins, and a grad student of his, Ralph Alpher, I believe. I got those right. That then went on to say, well, if there was this radiation-dominated era, there would be some sort of relic radiation left over. And so then that's where then the CMB was thought to confirm that prediction there. So while it is evidence for for a radiation-dominated early universe, it is also not, or I should say, the CMB can also still exist within the cyclical models for the universe. So like Sir Roger Penrose's cyclical model, that's why I think I'll be a little more specific of what the CMB is evidence for. You mentioned the conundrum with quantum physics. I don't know. But I think something interesting to think about is, right, we don't really have a way to conceptualize that initial event of the Big Bang, right? It was originally presented by, I think it's a Belgian Catholic priest and also astronomer, Lemaitre. And his idea was actually that at a certain point in time, you have this primeval atom that exploded and then seeded the universe. And so when we try to think about all of space, it's tricky because we're not thinking of all of space at a point in some sort of space, right? There is nothing, I don't even know, nothing isn't even the right word to use there, right? We can't even conceptualize what outside of this primeval atom would be. So really, all of your, right, if the laws of quantum physics still applied in that, I'll say, energy range, right? Then I don't know, maybe it's not actually a point in that little atom, right? It could actually have 3 dimensions in that sense. This is where it's like space-time is really hard to conceptualize because we only work in 3 dimensions and we're trying to work out or think outside of that. And then I really appreciated though all the I'll say parameters, the fine-tuned parameters that you brought up, because it does. Again, I would probably say those are still philosophical in nature, and yet evidence for the fine-tuning of the world that we live in. So, thank you.